let's start with our, like I have already started with my recording. Now, if we look into the presentation, right now, we'll look into that, the data. Now, this thing we need to keep into our mind, okay? It's very important. So, over here, what you can see that the input, this is a very good workflow for RNA analysis. Now over here you can see that inputs we have raw sequence data, annotations and reference genome. Right now what we have did is that we already have the raw sequence data which is present in FASTQ format, and we have zipped them so that we can use those one for a pre-processing steps. It means that we require the quality control. So if you look over here, we have got our data. That data is in the FASTQ format. Now it's time that we look for the quality control. Okay. Before that, first let's understand what is FASTQ. Then we will perform the quality control and we look into that how our data is. Okay. Okay. So over here, uh, I have created a folder by your name, and I have lot many things over here, but one thing you will see that we have these many sequences, right? So in my case I have all the 5 sequences. In your case you have 4 sequences. Okay, now what I'm going to do is that I'm just going to showcase you one thing, and we'll see that. Okay, first thing is that let's just look into the data, understand that what is FASTQ, then we will start with our practical part. So whenever you want to see anything which is in the zip, it's a zip, right? So for that there is a command known as zless. Let me just give a name, the number 74 1.gz. Uh, okay, I have missed FastQC. I'll show you again. Let me share this with you. Copy this, paste over here. So in your basically the files where you have your all files, if you basically run this particular command, okay, so what will happen is basically you will be able to see the data one page at a time. Okay, so you can see that this is my the snapshot of one page. If I use again a space bar, this is my second page, third page, fourth page, fifth page, like that. And if you want to exit from this one, you will press Q. So Q to exit, over here I'm mentioning Q to exit, you'll press Q to exit, and you'll press space bar for page for page. Now why I'm saying that, why I'm showing you this one, so that you get the idea that this is the data which we have downloaded. Okay, so let me just do it again so that you can see that we have this kind of data. Okay, can you see that? And again at the symbol, something has started. Clear with this part? Yes. Now let's look into that, what basically these lines are. Why this is important? Because in order to do the analysis, it is very important to understand this particular data type which we are dealing with it. So this is a screenshot of another sequence where you will find at symbol, which is also there in our data. You will find the second line, which is basically our raw read sequence. This is the one which we are more interested, right? Because we want the sequencing to be there. So sequencing is like that. In the fragment, it is reading that at this particular position, this base is present. So this is our raw read. We are interested into this part. Then the third line is basically known as spacer. In our case, we do not have the plus sign. There are tools we can convert that line. In most cases, what you will see that the whatever the ID is present on the first line, which starts with the at character, you will see the identification of this without the at character in the third line. Now, why third line is important? Because the fourth line is basically tells us the quality, because right now we are very much interested into the sequencing data. It's our most important thing, right? But we also want to have a confidence on how the machine is calculating it, like how good it has captured the information at that particular position, how accurate that call was. So to understand that how accurate it is, it provides us the quality score, okay, in a form of ASCII character. So in computer science, we have a standard way of writing the different characters which are present in our keyboard. So one is Unicode. The one they have used is ASCII character. What is ASCII? I'm going to tell you now in a bit. Sorry. But what you can see that they have highlighted that the column like capital T equal to colon, okay, and you can see that it is 25. Now we need to understand that what is ASCII character, what is 25, whether it's a good or bad. Just understand this thing. In this FASTQ1, Q stands for the quality. So FASTQ format was developed to provide a convenient way of storing the sequence and the quality score in the same file. Why this is required? Because our analysis is depends upon the data, the read sequence, and to have confidence about that the sequencer is doing its job in a nicer way, because I have told you that the machine has the efficiency of 97% or 99.7% of efficiency, and we only want to stick to the reads which are highly confident by the sequencer, so that based on the quality of the data we can actually filter out the data where which one the sequencer was not confident. Okay, so that's why this queue is very important. Let's just look into our own data. So we'll see that this is our first line, this is our the label, this is our read sequence which we are interested in, and over here they have mentioned that it is 101 length. Then you can see the plus, this is your spacer, and then you can see the quality score. So you can see capital F, colon, capital F, this kind of information you can see. Now let's just understand the quality score in much more detail. Before that, we need to understand that we are working with single end and a pair end data. Okay, so single end might will have one or it won't have one, and in the pair end it will have two. So let's look into our data because we are dealing with pair end data. So over here nothing is mentioned over here. They have mentioned like this, this one. Okay, so now let's just look for the pair, the reverse end, and let's understand that how it is showing us. So over here this is again the one. Just a second. And they have not mentioned anything over here. I don't know why, but they should mention this thing. I don't know why they have not mentioned it, but usually this is a case where we should get /1 and /2. Maybe some issue with this tool, otherwise it will showcase 1 and 2. but as we already remember that these are the two files, so that's why I'm not uh, keeping into that. But usually you will see /1 and /2 or n1 or n2 in the case. Over here we are not getting this one. So just remember that basically these kind of quotations we will look into that 1 and 2. Okay, so in our case it is not showing us, but in majority of the cases it shows us that 1 and 2. Okay, just to distinguish, because from this one fragment when we are doing the single end we are getting only one read. In the pair end, from the both the directions the fragment has been read, that's why we are getting read 1 or read 2, forward 1 or reverse 1. Now let's just understand the quality control. The quality score of a base is known as Farad or a Q score. The person who comes with the formula, that's why it's also known as Farad score or a quality score. It is an integer value represent the estimate probability of error. Like at the time of reading that particular position, how much the error was. So it calculates the error. So based on that, we can say that at this particular position, how much the detector was confident. Okay, that is that base is incorrect. So Q scores are often represented as SCI, that is the American Standard Code for information interchange characters. Okay, now let's just understand in much more easier way. So this is a Farad score equation. We don't have to remember anything. This is a basic uh, uh, like basic principle which works for to calculating the quality score, because the next tool which we are going to use basically calculates this score and give us the quality of our data, which is the must step we need to do in order to perform any kind of analysis, data analysis. Okay, so you can see that. So this table is very good. Over here we can see that if the value is 10, okay, it means that it has the 90% of base accuracy. If it is 20, 99% of accuracy. So in our data, we always want the value minimum 20 or more than 20. Why? Because the base call accuracy will be 99%. So we always want to retain the sequences which are at least 90%, 99% good or more than 99% of confidence. Okay. So now in the first one, if you see over here, they have mentioned 25. So 25 is more than 20. So it means that the base call accuracy is more than 99%. But in your data, you can see that the values are some symbols and basically the characters. How to know that what is the quality score? So for that, we have the SKI table. I've told you that all the information is saved under the SKI, right? So this is the SKI table. Now over here you can see that they have different character and they have a Q score. Okay, so now sorry, they have the characters and they have the Q score. So now if you see capital T, so where's the capital T? We need to search. So sorry, capital T is basically having the colon. So let's just search for the colon symbol. So if we search it, we can see that colon is present over here, and it is having the quality score as 25. So 25 is more than 99% of quality uh, confidence. So we can say that when the T was read by the detector, the machine, it was more than 99% confident. So it means that this particular position, this read has the high confidence. Okay. So these are the things which are be used by the software to calculate the quality of the data. Okay. And this is what we are going to do. So for an example, one more example, we have the at character. So now if I search for the at character for the GNC, so it's having the quality of 31, and 31, 30 is 99.9%, so more than 30 is basically more than 99.9% base call accuracy. So the quality score which we want is basically more than 20. Why? Because uh, less than 20 is below 99 percentage, which we do not want. We want our lead at least minimum 99 percentage. Now, why these numbers are important? Because when we start filtering out the data, we give these values to have the to retain the good quality of data and discard the data which is not in a good shape. Okay, why? Because our result is totally depends upon the data which we are using it. So we don't want to go with any data or any reading which has the lower confidence. Now again the question comes that either we are we losing our data? Yes, we are losing our data, but that data which we are losing somewhere cover in the remaining data, because whenever we are going for a sequencing, we are going for million reads many number of times. So there are chances that the data which we have loosened up below 20 might have been present in the data which we have restored. So this is very important. So always understand that we always use the quality score at least 20 or more than 20. Okay, not more than 30. We choose the value between 20 and 30. Why? Because quality score, quality control test, or the pre-processing steps which we do, it is at the initial level before we start with our analysis. So before we start with the analysis, we need to keep the value which is good, which retain the data quality, but it should not also discard the number of data, higher number of data. So that's why we always go with the optimum value, that is between 20 and 30. So this is a table, and all the machines, they uses these kind of information. Even I will show you in the Google that how the information you can get. Okay. Now this tool, FastQC tool, is the tool which we are going to use for the quality check. And we will look into the results, and you will have the idea that how we check the quality of our data. So this is how it looks. It is having different reports which tell us the information on our data. So let's just do it. Before that, any doubt? Clear with this part? mRNA will have na? Yes, it will be, these files will be large only, because transcriptomic analysis we need at least 20 million reads. We are looking for the gene expression, right? Even for some time the size will be 4 GB, 5 GB. RNA data is always big. The minimum you will get is basically uh, like the sequencer run for at least 20 million reads. For RNA, it is recommended. Okay, clear? Now let's start with our practical part. So now, okay.